Hello, my name is Hui Ling. Today I am going to talk about N-heterocyclic carbenes, which are also known as NHCs. First, I will talk about carbenes in general, after which I will talk about the modes of stabilizations in NHCs and the effects on their reactivity. I will then elaborate on how they catalyze umpolong reactions of aldehydes and microacceptors. And lastly, conclusion. So what are carbenes? Carbenes are neutral compounds that consist of a divalent carbon with 6 valence electrons. As the carbene-carbon has less than octet configuration, they are highly reactive species. They can exist in two different ground states, which are namely triplet and singlet states. For triplet state carbenes, the degenerate px and py orbitals are singly filled, and they undergo radical chemistry. For singlet carbenes, the carbene-carbon has a vacant p orbital, which is the LUMO, denoted as p pi. It also has a lone pair of electrons in the HOMO, denoted as sigma. The vacant p orbital can accept electron density, which allows it to act as a Lewis acid, while the lone pair can also be donated out, which allows it to act as a Lewis base. Its reactivity is dependent on the substituents attached to the carbene-carbon. As to which ground state the carbene prefer, it will depend on the size of the HOMO-LUMO gap. NHCs are cyclic carbenes where the carbene-carbon is stabilized by at least one nitrogen atom. They are singlet carbenes that act as electron donors primarily. And this is the first stable NHC isolated. Another example of NHC is imidazole 2-yllidine. The band geometry of the molecule breaks the degeneracy of px and py orbitals, causing it to adopt a sp2 type hybridization. The lone pair orbital is the HOMO, and the vacant p orbital is the LUMO. The carbene center is stabilized both inductively and mesomerically by the adjacent nitrogen. For the inductive stabilization, it can be explained using MO diagram. When the carbene center interacts with an electronegative atom like nitrogen, the energy of the HOMO is lower than when the carbene center interacts with an electropositive atom like lithium. Therefore, it shows that the HOMO energy level is lowered with nitrogen and hence more stable. For the mesomeric stabilization, it involves the pi donation of electron density from the nitrogen to the p pi orbital, which is the LUMO. From the MO diagram, the LUMO further interacts with one of the nitrogen atom, which then raises the energy of the LUMO. This widens the HOMO-LUMO gap, and hence, NHC prefer to be in the singlet state. The donation of electron density to the vacant p orbital also reduces the Lewis acidic character of the molecule, causing it to act mainly as an electron donor. NHC is a very versatile molecule. It can act as ligands for transition metals, form adducts with p-block elements for small molecule activation, and also act as an organocatalyst. Among these main branches of applications, I will be focusing on how NHC catalyze umpolong reactions. NHC can catalyze umpolong reactions of aldehydes and microacceptors. So what is umpolong? The inversion of reactivity of a molecule is termed umpolong. For aldehydes, the carbonyl-carbon is electrophilic, which can be attacked by a nucleophile. However, in the presence of NHC, homocoupling of aldehydes can be observed, with the red bond indicating the formation of the new bond. In order for this reaction to take place, the reactivity of one of the aldehydes has to be reversed. This is the proposed mechanism for the reaction. First, the catalytically active carbene is obtained from deprotonation. The carbene will act as a nucleophile and attack the aldehyde to form the primary carbene aldehyde adduct. The hydrogen on the adduct is now made acidic due to the negative inductive effect of the cationic azolium group. The adduct will then undergo proton transfer to form the Brestow intermediate and enamine-like intermediate. In the intermediate, it can be observed that the initial electrophilic carbon is now nucleophilic due to the pi donation from the heteroatoms on the carbene. The reactivity of the aldehyde is reversed here. It will then attack another molecule of aldehyde, and further proton transfer and elimination steps releases the product and regenerates the catalyst. For microacceptors, the carbon beta to the carbonyl is electrophilic. Hence, nucleophile will attack this carbon. In the presence of NHC, the reactivity of the beta carbon is reversed, allowing the formation of the new bond in red. This is the proposed mechanism. This is similar to what we have seen for the case of aldehydes. The catalytically active carbene acts as a nucleophile and attacks the beta position of the microacceptor. After the subsequent proton transfer step, an enamine light intermediate is formed. Now, the carbon beta to the carbonyl is now nucleophilic. Hence, umpolong of the microacceptor is achieved. The nucleophilic beta carbon will then attack another microacceptor, followed by subsequent proton transfer and elimination steps to release the product and regenerate the catalyst. In conclusion, these are the points that I talked about in this presentation. I hope that this can help everyone understand carbenes and NHCs better and appreciate their wide applications. Thank you. And this is the list of references.